So my talk is about reactive for the impatient. That's how I name it. The reason I name it is that the impatient part really is referring to us, like human beings. But first of all, let me introduce myself. Again, I'm a Java developer advocate at IBM by day. And then by night, I'm a Chicago Java Users Group organizer too. So I'm very much involved with the community. And then as a developer advocate, I travel to different conferences, even like all over the world now, and talk about different topics. And at the present moment, my topic is on reactive. So I'll get started. I guess I can't even see, but like maybe a few of you too. Have you, folks here, have you actually worked with reactive programming or reactive systems at this point? Or I guess I don't see many hands too, so maybe a few. Yeah, I can see a few. So bear with me if it's something that's more fundamental, because it's really intended to be really a gentle introduction to reactive programming and reactive systems. And then with the survey of the 4 common Java tools and libraries that are listed here. So first of all, I'll talk about like why reactive. So reactive itself is not completely brand new. It's actually, with the telecommunications industry, telephones and phone communications, there was already a lot of demand for real-time communications. And then there's also the actor model that actually came out in like the 80s, like out of Erlang. And that was actually kind of catered primarily for like telecommunications kind of applications too. So it's not really brand new. But why is it then all of a sudden we're hearing a lot about, like, say, React? There's React Native and then reactive really refers more to the Java side of things, reactive programming and reactive systems. And then React Java or React JavaScript and React Native, they are really coming out of Facebook, and they are more for like the JavaScript side of things too. So there's the differences in there. When I first stepped into working with reactive programming and reactive systems, that was when I joined IBM about 8 months ago. I also found it to be quite confusing. So that's why I thought I'd do a talk on more like what my finding is too, is as a more gentle introduction to this subject area. So yeah, let's see, why reactive? So basically, over time too, the hardware changes, level changes have kind of advanced like over the past, like maybe like within the past 10 years have really kind of been shot up, right? The advances. Right now, the CPU, there are like multi-core CPU and multi-CPU and hyper-threading, and the clock speed and everything has improved so much. So, and then also too, not even mentioning, right now we all know virtualized computing infrastructures, like the multi-cloud strategies, all the cloud and containers, everything too that came out. So that leads to more of the need for software to get caught up. So then it can take advantage, like better advantage, full advantage of what the hardware can offer too. So then like systems, for example, like Lightband that comes out with the Akka reactive systems, they really take full advantage to the actor model, is able to take advantage of this capability in the hardware and kind of making the user on the coding side less concerned with doing like multi-threading, because it itself, the actor model, is sort of like help with this kind of concurrency distributed programming model. Okay, so that's the side that's coming out of hardware and virtualization. And then on the software application level, think of too is that we as human beings, we are also like very impatient. And then also to think of how we used to have like no cell phones, and then we go to like maybe 1 cell phone per family, and now not even like 1 cell phone per person in the family, but each person may have multiple devices. So there will be like a need for multiple devices accessing the network and everything. So software itself needs to get caught up, so then allow all of our devices to be able to take advantage again of what the advances that are like on the hardware firmware level. And then the most important thing of all is because we, as human beings, we are really impatient, and reactive programming and systems really addresses the needs for the human beings, being more responsive applications that are able to respond in real time and freeing us up to do something else. So it's really designed for us, the impatient human beings. And then so now I'll go into talking about what is reactive. So there's this reactive manifesto here. I won't go into all the details here with this talk, but I like to point out to this link where it has description of all of, about what the reactive manifesto is. Essentially, too, is this. It's a set of guidelines that defines like what reactive systems should be, and it's headed by Lightbend. Lightbend, again, this company, if you are not aware of, too, they are based in, I think, Sweden, and it's started by the creator of Akka, or actually Scala, Martin Odersky, his company. So they developed the Akka systems, which is a reactive systems platform. And over there, too, they are also taking a lot of leadership in terms of defining what the reactive system should be, all of the principles. And essentially, to summarize, it promises more flexible systems that are highly responsive. And not only is it responsive, but also able to handle failures a lot more elegantly and also more tolerant of failures, too. And that's kind of very important, too, as we shall see. And so now I go into talking about the 4 core principles of reactive systems. First and foremost, responsive. So by being responsive, what we really means is that responsiveness really is cornerstone of usability and utility. So what it means is that systems needs. That's too much. Okay. Okay. So yeah, it means that by being responsive, it means that systems needs to be able to respond to a request comes in, and the response needs to be able to come back on time. Of course, too, as us human beings, we want things to be done yesterday, but it doesn't necessarily mean that in this case. It really means things needs to respond, requests needs to be handled in a very timely manner, is what responsiveness is too. It focuses also on providing like rapid and kind of consistent response time, and then establishing like reliable upper bounds, so they deliver like a consistent quality of service too. So that's a bit more like formal kind of description for that. And then, so first of all, again, we talk about responsiveness, then we go into talking about elastic. So elasticity implies like the scalability of a system. So if the load on a system, all of the requests coming in, increases, then your system needs to be able to respond in a very timely manner as well. And how? And it's really being done by the resources being, let's say you have a lot of requests coming in, then the system, a properly designed system will have good capability of managing and have more resources to handle all of the requests that comes in. And then if they're like, the system is kind of becoming idle, then all of these resources needs to kind of return back to the pool for doing something else. So it's got this kind of elasticity, scalability aspect of it, so that the overall throughput doesn't suffer, according to the load, is what elasticity is. And then the next thing too is actually the third principle is about resiliency. So that kind of deals with how there are failure conditions. So failure too in reactive systems is like a first-class citizen, meaning that as such, reactive systems are really like event-driven system. So failures come in, it's like just like another event, but it needs to be handled accordingly. And so resiliency really, it's also achieved like by replication, containment, isolation, and delegation too. So failures really are contained within each component, and then isolating components from each other. So then ensuring parts of the system can fail and recover without compromising the system as a whole. So, and also to recovery of each component, it's also delegated to another component, so then that assure that high availability too, and that can be achieved too for all of the responses. So, and then overall too, basically the systems will need to stay responsive to during like the whole, the whole lifetime too. So. And so those are the 3 kind of basically the core principles first, and then, oops, sorry, I think I go a little too fast. So essentially, too, then those are the 3 principles, and it's all enabled by systems having a message-driven kind of aspect to it too. So by message driven, we really means that messages are being delivered to some known address too, in this case. So because in any reactive systems too, like all of the components are being isolated in time and space and resource. And so there's then got to have, all of them needs to be able to communicate with one another. And in order to do that, then your systems, the mechanics part needs to have this message-driven capability to it too, is what it is. So let me kind of make sure. Okay. And so essentially too, the message-driven too is basically asynchronous message passing too. And that provides like location transparency, and also like helps with like back pressure, because if there are back pressure built up too, then your systems also needs to be able to handle all of the pressure and kind of maybe like reducing the number of inputs at the same time, or maybe having more resources to handle all of your requests. So that's all like in message-driven side of things. So okay, so now we'll get to the next slide. This actually talks about here I am like using a diagram of a picture of fruits, because you can look at fruits, they look like they're all fruits, but they are not really the same. So there are differences too between like reactive programming and functional reactive programming and reactive systems. So first of all, the reactive programming. In reactive programming, what drives like in the flow of the logic is really driven by this change in the state of the data. So the data in your event-driven system. So data comes in and data get transformed. So that gets transformed and it drives the logic forward. However, in functional reactive programming over here, what drives it forwards? It's really the thread of control. So there's in functional programming, you have the thread of some logics happening. So the thread of execution continues. That's what drives the logic to go forward. Whereas in like now we get into reactive systems and architecture, that actually we're talking about bringing reactive systems, reactive programming and systems to another level of reactivity. Here we're talking about systems as a whole. We're managing many different components. So that's got to be ways of managing all of these components so that they don't step onto each other, or if there are heavy loads, there's got to be ways of handling it accordingly too. So that's what reactive systems architecture is. It addresses the whole ecosystem. Whereas like reactive programming, go back to here, it handles like a single component. It deals with like a component, reactive style of programming within it, and all the internal logic and managing the data. So. And here too, I also have another slide, which I actually borrow from the Lightband architecture. So here it kind of compares like event-driven and message-driven. So the main differences between the two is that in event-driven, as you can see, it's like a soapbox, right? So there are events that comes out. It's like a soapbox announcing some events that come out. It's like the old like publish, subscribe model. So you have messages that come out, and it's being events. They're being like announced. Some things happen. It doesn't have an address. It doesn't say who the messages go to. It's just being kind of almost like broadcasted, kind of emitted, kind of like that, without any destination. But it's up to the observers. In this case, whoever is interested, the specific like people listening on it, will actually respond to it accordingly. So that's event-driven. Whereas like in message-driven, then we're talking about message-driven having recipients that are kind of addressed that are known. So basically, message-driven communication really has an addressable recipient and also a single purpose is what it is. So here too is that I replaced the original diagram. They're saying two persons talking in here because you know where your messages is going to, but it's almost seems like it's like envelopes. It's much like if you work with soap, right? Web services soap. It's like soap envelope. You have actually address to where the messages go to. So those are kind of like the primary differences between the two. Okay, so now it's almost lunchtime. I thought I'd put a slide up so then everybody's not falling asleep yet with all the boring concepts. But here too, I'm kind of, I wanted to talk about like, as I'm kind of working through this, I'm thinking of like use case. So I was actually in Japan for the Java Users Group conference back in December, and I went into the ramen shop. So, and I was kind of doing research too on reactive systems and programming, getting ready my slides for the year and presentation. So I was thinking, oh, that might be a good use case to adopt like reactive programming and reactive systems too. And I'll explain why in a little bit. But just thought I'd kind of pique your interest first, and it's almost lunchtime, so you won't fall asleep. Okay. Oops. Did I do it right? Why is it not advancing? Okay. Sorry. So I'll just go back to talking a bit too about some of the concepts right now. So we're going to reactive programming first. So some patterns and terminologies here. So I bring up reactivity. So reactivity is really the process of responding to external stimuli and propagating events. And then events are really the stimuli in this case. And then streams are the primitive representations of a sequence of data elements. And observables, especially if you kind of using like RxJava, also like using like the Spring Reactor. Actually, Spring Reactor is using Flux now, but in Rx2 reactive extension, there's observables. They are really stream of events that we are referring to. And the design patterns that I used here are observer, composite, and iterator patterns. So those are kind of commonly used, like especially in Java too. These are the patterns that are being used. Here, I'm also here borrow some slides too from the Rx marble diagram to explain a bit about reactive programming using this timeline. So in the very top one, over here, this is just a timeline. It's like a stream, but over here is that there are no events that are happening in this stream. It's an open-ended stream in here. And the second one here, you see some shapes, and these are like some events that are happening, and then all of a sudden you see this perpendicular line. It indicates that the stream has terminated, so there's some definite time like limit to this stream. And then the third one over here, you see some events that are happening on the streams, and all of a sudden you see like a cross in here. So the cross really indicates it's a failure events. So failure itself is a first-class citizen, so there's no difference than other events that are happening on that stream. And so this would indicate that your systems will need to handle it accordingly. And then the very bottom here is that it's essentially an open-ended stream because you have the stream keeps kind of being there, and then there are different events that are happening, but there's no end to this stream. Okay, so now I'll bring you to the next kind of example of just using a commonly used map transformer. This is the function to explain a bit about reactive programming. So over here in the top there, using that timeline, we have like 3 events and 3 kind of data that comes in. So 1, 2, and 3. And then over here, we are applying this transformer, this function transformer, a map. So the map itself, what it does is just transform. It tells it's a function. So what it does in this particular example here is just a basic case. It takes the input and multiply it by 10, so 10 times x, and returns it. And then so you see it in here. After the transformation, you see that this timeline will become, the 3 original data elements will be transformed, and then 1 will becomes 10, and then 20, and 30. And to put it in code, then over here in like RxJava, that would be observable.just. So that's like the .just is taking in the input. So 1, 2, and 3 in this case. And then apply .map, and then give it the function definition to it, multiply by 10. And then you immediately do a subscribe. So this subscribe is essentially the consumer of what's being produced. So you can see too, actually, the reactive programming as compared with like imperative traditional programming is a lot more elegant in this case. Because if you think of normal imperative style of programming, you need a lot more statements to handle all of these. You need to parse your input and then basically then apply the transformer and then print it out in separate statements. But here, you can actually group all of them, and taking advantage of Java 8 and above capability, streaming and functional programming, you can actually group all of these within one single statement in here. So you do a subscribe in here, and over here too, all it does is using just timber and basically print out the result. So you then see, if you put it and run it through, you see item 10, item 20, and item 30 in here. So if you want to see more of these transformers for Rx, you can actually go to this rxmarbles.com. It has a bunch of like interactive usages too. There are other transforming functions such as like filter or flat map and things of that nature too. So you can see to it, it's actually, if you process a lot of data, you apply this style of reactive programming, it actually can be very elegant too. Okay, so next I'll go into talking, after some programming, we get into the reactive systems design. So I, again, won't have time to go into all of the patterns, but because reactive systems, we're dealing with systems as a whole, there are many components. So there's some ways that we need to manage them. So these are the different patterns that are kind of categorized, yeah, into these essentially six larger patterns. They are state management and persistent patterns, flow control, and then the message flow, and then fault tolerance and recovery, replication patterns, and resource management too. So some of the state management patterns will have things like domain object and sharding and event sourcing and event stream. Flow control, then you get like pull and then manage queue, drop, and throttling. Message flow, you can have request response, ask pattern, aggregator, the saga pattern, for example, business handshake. Fault tolerance, you can have like circuit breaker, for example, and replication patterns that you can have like active passive and active active, things of that nature. And then let's see what other interesting, yep, that's right. And then we'll talk a bit too about the circuit breaker too in the next slide. So here too, yeah, a few more like terminologies too. So there are also like reactive microservices too. First, there's microservices. What microservices does is that you break up your systems like from a monolith into smaller kind of chunkable size. And so you make your management of your systems a lot more easier in the sense that if you want to update one part of the system, you don't need to bring the whole systems down. That's the idea. That's one big advantage of doing things like in microservices style. So there's also reactive microservices, which you apply the reactive systems kind of approach to developing these microservices in a very asynchronous, non-blocking fashion. Again, reactive systems, we're talking about isolating all the components, isolating them in state, in space, in time, and failure. And there's also the circuit breakers pattern. And that one, essentially, it's basically you're handling the recoverability of a system, resiliency. Because if there are failures that occur, then you need to have some ways of breaking this failure, stop it from propagating itself. So that's circuit breaker. And there's back pressure. For example, too many requests coming in, then it builds up like a back pressure. So then essentially the components that are under like so much pressure, for example, cannot handle it. And then say, for example, in Akka, it has this supervisor capability that basically components can then notify the supervisor actor and said that, well, I'm under pressure. So the actor model, essentially the supervisor should then maybe spin up more actors to handle all the requests, or maybe like slow down the input. That's the idea of like handling the back pressure. And then there's also high availability and eventual consistency. And also this CAP theorem, too, just want to quickly bring it up. So CAP theorem talks about three aspects in any kind of data systems. One is with the network partition, and also then with the high availability, data availability at all times, right? And quick response. And then also consistency. And the CAP theorem basically says that of the three aspects of this, three aspects of any data-intensive system, only two can happen at the same time. And then network partition is always a given. So then high availability and eventual consistency, they cannot coexist. So which means in order to be responsive, maybe sometimes you can kind of sacrifice a bit of your data being consistent, because we believe that eventually data won't be constantly being updated. So then over time, your data that gets returned will become consistent in that sense. So yeah, so if you're interested, go into that book. It's actually, I have the link at the ends too, that talk about reactive systems design that goes into talking about these eventual consistencies, which is actually quite interesting. Okay, and then another quick thing to point out is about reactive streams too. Quick one line over here in the middle is that this is really a standard for asynchronous stream processing with non-blocking back pressure. And it's a specification currently at 1.0, and a group basically essentially is led by Lightbend again, and with the other companies. And it's actually latest release in 2017. And RxJava supports this kind of almost all of it, and then Spring Reactor supports it fully. So is Akka too. So, and then how about like microservices? A quick thing too. So reactive programming is being used within a single microservice because it's used for implementing service internal logic and also manage the data flow. And then reactive systems are being used in between the microservices because it's because of its message-driven capabilities. So it bridges all of the communications between all of these components within a reactive systems is what it is. So then that enables, again, going back to the three principles, the responsiveness, elasticity, and also recoverability of a system. So. Now, also another thing I like to point out is the reactive microservices framework that comes from Lightband. So it's built on Akka. This is called Lagom. Lagom is really again, reactive microservices framework. It has like RPC style programming support, and also has a message broker API too that's implemented in Akka streams and Kafka. And the persistence is based on concept of entities domain-driven design. So event sourcing and CQRS, which is command query responsibility segregation. So we can talk about it more too if you're interested later. So. And okay, so I'll go back to my use case. Yeah, I was just earlier, I was talking about the noodle shop. So going into that noodle shop and in Japan, if you've been there, you go in and it's basically there's no server, no specific tables or chairs. You go in, there's one vending machine. So as you can see, when it's dinner time, a huge line of people wants to have noodles. Go in and then they have to punch in their order in one single vending machine. You wait in line, then you put in your money, you get your tickets of what you order, and then you give your orders over to the server. And you sit around like a bar area. You sit around. So you have to wait for a space to open up before you can sit down. So as you can see, this kind of, I immediately thought of it so like kind of in a computing terms, it's so much about reactive programming in that reactive computing kind of paradigm. Because the old style in here is very blocking. So you have only one machine, everybody wait in line. There's a lot of wait time that are wasted. I mean, think of us programmers especially, right? We don't want to waste time. We want to have things like immediate, like responsive, or maybe we're doing something else while we place an order. So that's my idea too. So my idea is that I scribble on a piece of napkin, so now I put it onto slides, and basically was thinking that, well, if using reactive computing paradigm, we have like over here, we're customers, we come in, we place an order, those are observables. But look at this, the order system can actually be a mobile app. So it takes order. So I'm a busy programmer, I'm hungry, I just thought, okay, I want to go to this ramen shop and then order my food through the mobile app. And then in the meantime, I'm not being blocked. So as I place an order, the order goes out. The observables are being observed by the waiters, essentially, the waiters in there waiting at the restaurant. But in that case too, they cannot actually tell the cook to cook noodles yet because you need a seat to be opened up. So there's got to be another observables coming from the seat. Once they open up, then you have another events that kind of notify on your observables. Okay, there is seat open up. So basically, the waiters will then, the observers, waiter, will have to see that, okay, there's order coming in, there's observable from the seats. Then now, put the two together, then I can tell the cook to cook the ramen. So when the ramen is being cooked, and basically too, there's observable too, coming from here, the observables is basically when the noodles are ready, then it comes in here, and then when it's ready, then it basically will notify us who are like hungrily waiting for the noodles to happen. So yeah, so this kind of in a sense is not is not real life, but it's just something to illustrate that so much that system can actually be used, or we can actually employ like a reactive programming style to develop this system, because then it relieves us of the time to have to wait. Things will become non-blocking rather than blocking in that sense. So that's an example too that I just wanted to share. Okay, so now the last part of this presentation just goes into, let me quickly go over now. I think it looks like I probably have little time left. But first of all, the four tools that I want to talk about, RxJava first. That's actually a Java implementation of ReactiveX. And it's very popular, especially in Android. And also is available too. It started out reactive extension for .NET in Microsoft too, and then Netflix ported it to Java. And basically 2016 comes out with flowable and back pressure as well. So the current version is still RxJava 2. And then a very simple example in here is just a hello world to show it. So look at 2 in the programming. Again, you can chain all of the commands together in one command statement. Using Flowable, you do a dot from array and takes in your arguments and do a subscribe right there. And the subscribe will then just system output, do a hello world, a hello whoever in there. And this one too is also a quick one, but I actually already show it too. Is basically I just wanted to quickly show producer is observable.just, and then the consumer, in this case doing a system out print line. And basically to attach the producer to consumer, all you need to do is do an observable.subscribe and then pass in the consumer. And that's RxJava too. Okay, so now I'll go into Spring Reactor. So Spring Reactor comes out of Project Reactor from Pivotal, and it's very similar API to RxJava 2 because the two groups of people, they're similar groups of people that develop the two libraries. So, but Spring Reactor came out since Java 8, so it has a lot more support for the streaming Java 8 and has a bit more cleaner interface too. And just a quote in here too, David Kanok, who's the engineer for both libraries, he said that to use Reactor 3 if you are allowed to use Java 8 or above, and then use RxJava 2 if you're stuck on Java 6 or need your end functions to throw checked exceptions. And then these are just a set of all of the libraries coming out of the Spring Reactor. The core is the one that you use for developing your apps. And there are other integrations, say with Netty, with Adapter, Kafka, and RabbitMQ as well. Okay, and here is an example too of Spring Web Reactive. So this is a non-blocking web stack. So using traditional approach, you think that the two sets of approach look the same, but they are kind of different too behind the scenes, right? So the top one here is the traditional approach, is a blocking call. So basically, if you run this, then you see the system output print line, print out traditional way started. And then over here, then the call will be blocking, going out to get the list of products. So then it waits for the list of products to come back, then it prints out traditional way completed. However, if you use the reactive approach using Webflux, then what it does in here, the system output will say reactive way using Flux started. And then basically then this call going to get the product stream. And then in this case, it returns you a Flux. So think of Flux as just like a ticket. You hold on to it. You haven't got your list of return Flux products yet. And then what you see is that in the runtime, then you actually get this line first, reactive way using Flux completed. And in the meantime, basically your client can then hold on to your Flux, and then kind of when the set of products is available, then you handle it accordingly. So that's kind of the non-blocking way. Okay, so that's just a quick example of this. And also a very quick comparison between the two, but I think I already talked about most of it too. But essentially too, the differences, like Spring Reactor makes use of Flux and Mono, and RxJava has RxJava 2 has observable and flowable and back pressure too. Okay, so, and I have my slides available too, so. Yeah, so now I'll go into talking about Akka. So Akka is again from Lightbend, and IBM has a partnership with Lightbend since in June 2017, so almost 2 years ago. And Akka makes use of the actor model that actually originated from Erlang, from actor programming model in the 80s. It's event-driven, location transparency, lightweight, and the resiliency, recoverability is really greatly, very powerful. It's done by the supervisor capability. So over here too, quick example too of a Hello World implementation. You see that in Akka is a bit more coding because of the use of the actor model. So in this case, in my main, all I do is basically instantiate my main actor class. In this case, Hello World. And then if you look into the Hello World in here, so just quickly point out is that the Hello World will extend your abstract actor. And basically, it goes into the pre-start. The pre-start is basically over here. We'll start another actor in here, which is called the greeter. So basically, it creates the greeter class in here. So again, I'm just doing it quickly in here. So if you look into the greeter class, so all it does here is that it basically it gets started up. It doesn't do anything until a request comes in. When it comes in, then all it does is print out Hello World, and also then return print it itself out, right? Basically, yeah. So, okay. And then this one too, just a quick example is how it is being done in Scala is a lot more cleaner too than Java in this case. So if you do any Scala, this is how it's being done. Okay, so the last comparison in here is actually to show in here is vertx. So that comes from Eclipse. Vertex, the nice thing about it is a very polyglot framework. So you basically can have Vertex and also then incorporate and with other libraries, with JavaScript, with Ruby, with Scala, anything. So that's a really flexible framework it has, and it doesn't have an actor model, but it uses what is called verticals. So there are components that are being deployed and executed by Vertex. And it's event-driven, and it runs only when they receive a message. And there's that Vertex event bus. And it's not restrictively tied to any container. So it's very flexible. And this is an example, too, of Hello World being done in Vertex. So you can see, too, it's also like very clean. You chain all your commands together. Essentially, Vertex do a create HTTP server and basically do a dot request handler and takes in your requests and basically then do the request dot response and then hello world. And then you also do a dot listen. You bind the HTTP server to port 8080 in this case. So this is a simple example for a hello world in Vertex. Okay, and so now I think I have 1 minute left, so a quick recap and takeaways. We already talked about some of these, but I do want to point out is that reactivity to this day is not fully been all realized yet. The reason is that on the database level, the database engine, especially relational database, there's no truly non-blocking database yet, I/O system. So even though we said that, okay, they're reactive systems, but when there are also reactive database connectivity library. For example, Pivotal comes out with R2DBC, and that one is a reactive connectivity library. But that one too, it's only for connectivity. So when you get to the database level, that you're still waiting for the database to process things in a very blocking manner. So that's something I want to point out. And something too, I'm also trying to get hold of some of the database vendor and researcher in there to kind of ask about if there will ever be database perhaps like making use of non-blocking I/O. So you can stay tuned too if you follow me on Twitter, because I'm going to do also an online virtual reactive user group too, and I'll be trying to get some of these speakers that I can interview them on the program too. So. And the very last thing, thank you very much for coming. And this is my Twitter handle and how to contact me. And also, I'd like to invite you, if you're interested, to sign up for the IBM Cloud. Over here is the link. IBM Cloud is free. There's a free tier access that doesn't have any time limit. So if you sign up for it, there are also free tier usages on some of the components on that, underneath the IBM Cloud toolbox too. So, and then there's also links to the IBM. We have technologies like reactive systems. That's the area I'm working in. We're intending to kind of beef up that whole section of materials in here. And also Akka, the Lightband folks, to also contributing some of the materials in there as well. And then these are some of the links too about the Lightband and also Reactive Manifesto and the reactive design patterns too, if you're interested. Okay, and then, okay. And also one small thing too, to just want to point out, I'd like to invite you to, there's an IBM, we have this initiative called Call for Code. Call for Code here, if you visit this link. So this is an initiative, a hackathon, a global hackathon. You can join as individual or maybe a teams of up to 5, and you can design systems that essentially is for natural disaster preparedness or kind of how to handle if there's a disaster strike. There's some ways of communicating and that type of stuff. So it's very creative. So, and there's still, deadline is open until July 29th, so there's still time too. So I'd like to invite all of you to check this out. And with that, thank you very much. I, again, want to thank you again for coming to my talk. And if you would like to follow me, please do so, and I'll follow you back too, and we can continue this reactive conversations. Thank you very much.